Hey everyone, I'm really excited about today's lesson. We're going to be talking about elevators. So what this is going to look like is first we're going to talk about why do we even care about talking about elevators? We're going to go through some basics about what's happening when you're staying in an elevator. I'm going to show you a video that I took in the elevator just earlier today, and then we're going to do two practice problems. So first, why are we talking about elevators at all? So we just learned about Newton's second law, the FAM law, and elevators are a really clear example of what's going on with the FAM law. Also, elevators are nowadays pretty common. So it's really cool if you are, next time you're in an elevator, you can try to think about what the physics is going on there. So you can go out and find an elevator and then feel the physics. Also, elevator problems start pretty simple, like we can talk about the basics pretty easily, but then we can have some pretty complicated elevator problems to really test your understanding of Newton's second law. And last but not least, when we're talking about elevator problems, we're not just talking about elevators. We can generalize the conversation we're going to have today to a bunch of different examples. So that's why this lesson is really relevant to what we're talking about. So let's talk about just the very basics of what's going on in an elevator. When we're talking about these problems, we can look at one of three different systems. We can look at just the elevator all by itself. We can look at just the person standing in the elevator, or we could look at the system of the elevator and the person together. By looking at any one of those three, we could see probably very similar things through slightly different ways. But for the conversation today, we're going to focus just on the person inside the elevator. So this is going to be our system. And importantly, when we choose this as our system, one of the things that we can then start to ignore is the force by the cable or by the tension pulling up on the elevator itself. Because thankfully, the cable is not in any way in contact with the person. Actually, when we look at the forces that are acting on the person, we see that at any point in time in the elevator, there are only two forces, which goes back to what I said about these problems can start really simple because at any point in these problems, there are only two forces acting on the person. We know that because a force has to be acting by an object on another object, and the only thing that's there to push up on the person is the floor. So we're going to be talking about how force normal changes at different times in an elevator ride in a pretty interesting way. But the important thing here is that the only two forces acting on a person in an elevator are the force normal by the floor pushing up on the person, and then the force gravity by the earth pulling down on the person. And so here would be the force diagram if a person were just standing in a stationary elevator. You see in this example that force normal and force gravity are balanced. That makes sense because if you're just standing in the elevator and it's stationary, then you're going to maintain your constant velocity of 0 meters per second. So the floor has to push up as much as the earth is pulling down. Now then, I want you to just think for like 10 seconds about what would happen if, let's say this person standing in a stationary elevator is standing on the ground floor and they want to go up to the top floor. So they reach forward, they push the button for the top floor, the doors close shut, and then what has to happen? Hopefully you recognize that there has to be an acceleration in the upward direction. In order for there to be movement in the upward direction, to go from stationary to moving in the upward direction, there has to be an acceleration in the upward direction. In order to cause an acceleration in the upward direction, what has to change? Well, since there's only two forces that are options, one of the forces has to either get bigger or smaller. In this example, the force normal actually gets bigger. The reason the force gravity doesn't change is, remember, force gravity is equal to -10 times the mass. So over the course of the elevator ride, the mass of the person is not changing. So the thing that needs to change is the force normal. What actually happens is because of the machinery going on that makes the cable pull up, the cable pulls up on the elevator, and as the cable pulls up in the elevator, the floor of the elevator pushes on the feet of the person, like basically extra hard in order to cause the person to accelerate. It's really weird to think about the floor like pushing up on you extra hard, but that is really what happens in order to cause the person, you, to accelerate upwards. So the normal force increases to cause the upward acceleration. And you'll notice in all of these examples, one important thing is that in every single one of these examples, I have the equality mark on force gravity, just to show you that force gravity is a constant for the entire elevator ride. You are not gaining or losing mass over the course of the elevator ride, so your force gravity is not changing. Okay, so one other thing about elevators is you don't want to be accelerating up for the entire time, because then you would just be going faster and faster and faster, and it would make the elevator ride dangerous. So the elevator only has to accelerate for a short period of time, and then it can just continue to move up with a constant velocity. When it continues to move up with a constant velocity, the forces can go back to being balanced. So for most of the elevator ride, we go back to this balanced forces situation in which enables the elevator to continue to move up, this time just at a constant velocity. But then we start at the ground floor, we accelerate upward. Now we're moving with a constant velocity and we're approaching the top floor. As we approach the top floor, we need to slow down so that we can arrive at our destination safely. We want to slow down to a stop at the very top floor. So in order to slow down, if we're moving up, we're going to need a negative acceleration. And again, just a little time to think about what needs to change about the force diagram to cause this negative acceleration. So again, the force gravity is going to stay the same, but we need to have a net force in the negative direction. To have a net force in the negative direction, my force normal is going to need to decrease. So it's basically like earlier the floor was pushing on you extra hard, and now the floor it's still pushing up on you. It's not like the floor has disappeared or anything, but the floor just like lets up just a little bit. It pushes up not as hard in order to allow you to slow down. And it's really cool the way in which this happens. You slow down for a little bit, and then all of a sudden you arrive at your destination. The elevator comes to a stop, the doors open, and when it's stationary again, the forces go back to being balanced. So that was kind of a big overview of what happens on an elevator when you start at the ground floor and move up to the third floor. And I haven't enumerated it here, but I would like for you to think about what would happen if you then got in the elevator on the third floor and went back down to the ground floor. It would be a very similar sequence of events, but kind of reversed. If you're up high and you need to go down, then the first thing you're going to have to do is experience a negative acceleration. And the thing that I like to talk about there is if any of you have ever been on the Tower of Terror ride, it's like the floor is dropping out from underneath you. Obviously, modern elevators are not like the Tower of Terror ride because the floor doesn't totally drop out from underneath you, but it does drop out from underneath you just a little bit. It's kind of like controlled falling. So it's not that the normal force completely disappears. It's just the normal force lessens by just a little bit. So when we're doing these kind of problems, to actually like quantify everything that's going on, we talk about we want to put numbers associated with the force gravity and the force normal force. So one of the ways that we put numbers with normal force is often elevator problems might mention standing on a scale. And the reason that elevator problems might mention standing on a scale is because, remember from last semester, scales read normal force. So if a problem asks you, what is the reading on the scale? It's really a different way of asking, what is the normal force in the elevator? And sometimes people do get confused because when you stand on a scale, more often than not, you're looking to figure out what is your weight, aka what is your force gravity, which is why when you use a scale, we really want the forces to be balanced. You shouldn't stand on the scale and bounce around, or you shouldn't be pushing down on the elevator counter, because that's going to change the normal force, which is not going to give you an accurate reading on your weight. If you use a scale properly, the scale always reads the normal force, and if you use the scale properly, that normal force is equal to the weight. So before we do a couple example problems, I just kind of want to show you a video that I took of me being in an elevator, just to show you that what I'm talking about isn't totally made up. So I got in the elevator at school, and I was on the second floor, and I pushed the button up to the third floor, and the doors open and they close, and I pushed the button to go back down to the second floor. So I want to show you a video of what that looked like. Specifically, I have an electronic balance with a 200-gram mass on here. Now, I will note that this is an electronic balance and not a scale. So this one is going to be reading the mass instead of the force normal, but the same rules still apply. We can just take this mass, divide by 1,000 to make it in kilograms, and then multiply by -10. But the numbers aren't really, the exact numbers aren't really important here. What I want you to focus on is how the numbers change. So at the beginning, I have a 200-gram mass, and my scale is reading right at 200 grams. And then when I push the upward button, I want you to see how the numbers change a little bit. So so you can see my hand moving forward. I push the button, 199.88 reading, then goes up very briefly to 220 newtons. And then you can see almost immediately goes back down to 199. And all of a sudden, just like that, we got to the top. Did you see that? The reading went down a little bit. We're stationary at the top right now. I'm about to push the button to go back down. We can see how the numbers change. As we accelerate in the downward direction, they drop again, then right back to 200. And then we're about to arrive at the second floor. You can see the numbers pop back up and then back down to 200. So just one more time, maybe with a little bit less of me talking. I will go back and then forward again. To show you this one more time. Remember, we started the second floor, go up to the third floor, and then come back down. So this is second floor. Accelerating upward, back to a constant velocity. Slowing down, stationary at the top. The door opens. Press the button to go back down. Accelerate downward, and then constant velocity again. It's really cool. And then we slow down to arrive at the second floor safely. So that's what an elevator looks like if you get in an elevator with an electronic balance. And then just to wrap up the lesson, the last thing I'm going to do is I want to take us through two practice problems. The first being a little on the easier side, and the second being a little bit more on the complicated side. For the first practice problem, let's take an 80-kilogram person, have them stand in an elevator. It looks like this person is going to be at the bottom floor and wants to accelerate upward with a rate of 2 meters per second each second. And the question is, what does the scale read? Which is another way of saying, what is the normal force? The first thing to do with all of these Pham law problems is to draw a force diagram. In this case, since the person is accelerating upward, we want our force diagram to have more normal force than force gravity. Then we're just going to apply the Pham law, which is that the net force is equal to the mass times the acceleration. Obviously, in this situation, we're looking at the y direction. So if you want to put a subscript on the net force in the y direction and the acceleration in the y direction, that would be fine too. But for the purposes of this, we're clearly just looking at the y direction. So the net force in this situation is going to be the sum of all the forces. So that's going to be force normal plus force gravity is equal to mass times acceleration. The problem is asking for force normal. So that's what we're going to solve for. In the problem, we're given the mass, we're given the acceleration, so we can just plug those right in. And we have to remember the formula that force gravity is equal to -10 times the mass. And that gets us to this step. Force normal is equal to force gravity, which is -10 times 80, or -800 newtons, which is equal to 80, which is the mass, times 2, which is the acceleration. Using a little bit of algebra, adding 800 to both sides, we get that the force normal is equal to 960 newtons. And that is how you do kind of the first level of an elevator problem. I'm going to ask you to do a couple of these for homework tonight. And then also, I'm going to ask you to do one of the more kind of extension level elevator problems, which is like this. Again, we have a person standing on a scale in an elevator, and the elevator is accelerating in the downward direction at a rate of -3 meters per second each second. We're told the reading on the scale, which is 700 newtons, and asked for the mass of the person. As with all of these problems, we want to start with a force diagram. In this circumstance, since it's accelerating in the negative direction, it's going to have a net force in the down direction. So the force normal needs to get smaller in order for that acceleration in the negative direction. And we start again with the Pham law, and it looks almost the exact same. It looks the exact same. Force normal plus force gravity is equal to mass times acceleration. Now, in this problem, we are told the force normal is 700 newtons. That's what the scale reads. And we're told the acceleration, but we don't know the mass. So it might be a little tricky, but what we're going to do is we're going to plug in the force normal, and we know that force gravity is equal to -10 times the mass. That's going to equal to the mass times the acceleration, or the acceleration times the mass, depending on how you want to write it. And so then hopefully you look at this and you see that this is an equation that only involves one variable, and still we should be able to solve it. 700, and we want to isolate m, so I want to combine all my terms for m. So I'm going to add 10m to both sides. Adding 10m to the left side just leaves me with 700 over there on the left. And adding 10m to the right side, -3 plus 10 is going to leave me with 7m, m being the mass of the person. Then isolating m, I can find that the mass of the person is equal to 100 kilograms. Those are our two examples, and that's the lesson for today. So I invite you to try a couple problems on your own for homework. Please write down any questions that you may have, and I can't wait to talk about this with you next class.